No. Well, hello everyone. Let's start with our discussion this week. This week we will focus more on the algebra, Boolean algebra. We will do many exercises on that, which I think was part of your second lecture this week. I guess the part of logic gates, we already saw a little bit of it on last week's in discussion section. And we'll have some exercises that deal with a little bit of that, but it's mostly about Boolean logic. And let's start. So with respect to notation, there are many ways of expressing Boolean logic. Again, we have our three fundamental logic functions. Let me think this. Yeah, let me. So we have our three logical functions, basic logical function. We have certain operators that define this logic function. You know? For example, with AND, we can use ampersand. We can even use this notation of function. No? We can also use these different operators, like if it were like a multiplication, and we have a series of AND operations, we can use this I guess operator, no? As if it was like a multiplication of a series of terms, no? But the reason we are making you use these operators in the first row is because it is easy to use it with our keyboard. Like it's not that easy to put this symbol with our keyboard or this one. And not only that, but for our autograder, like this is the way we are just evaluating expressions. No? So please, I guess, just use these operators that are in the first row, as that would allow us to autograde and make evaluations easier for us. But again, we can see that the AND usually is mapped to operators that are similar to multiplication. The OR are mapped to operators that are similar to the sum operator, no? And also when it's a series, we have this sum operator, and the not, well, there are many ways of doing the not. But again, let's stick with these operators that are in the first row, no? Yeah, so let's now go to the recap of the Boolean algebra properties. And these are very useful because through this we will be able to reduce any complex Boolean expression. And again, remember that reducing these Boolean expressions allows us to create more simple circuits, and therefore we are not consuming that much resources like monetary resources or energy resources, creating these complex circuits when we can reduce it and use less amount of gates, no? So I guess Boolean algebra has some properties that are similar to ordinary algebra. You know, we have commutative is similar, for example, but not all properties are the same. No, like, does anyone? So commutative is a property that is both in ordinary and Boolean algebra. No, I guess there's no problem with that. The order of the operands doesn't matter. No, when you have a certain operator. Associative is with respect to parentheses, no, like doesn't matter if you have something in parentheses, if it's of the same operator, the order doesn't matter. But what about distributive? Does it also apply to ordinary algebra? Anyone want to guess? If you replace the ampersand with a multiplication operator and the pipe symbol with a sum operator, like do these both of these properties apply?
No, not really, because the plus addition doesn't really distribute like that.
Exactly. Well, in this case, well, in this case, yeah, like with the multiplication operator, you can indeed distribute, no? Like, if this was, for example, the how to say, the multiplication, you can see that, yeah, no, you can do this, no? But the opposite, you cannot do it, no? Like, you cannot just try doing this, no? This doesn't apply to ordinary algebra, no? So yeah, you can see that Boolean algebra doesn't really necessarily conform to the properties of ordinary algebra. I guess, is there any problem with this? Why is this I guess this is a problem. Okay. So we also have idempotence, or however it's pronounced. X and X is equal to X, and X or X is equal to X. Like, do everyone understand why is this? Like, what happens if we have X equal to 0? What would this result in? Oh, okay, 0, no, because the X is 0, no. Why does it? What's 0 and 0? What is, if you remember your truth table? 0 and 0 is 0. Then 1 and 1 is 1. Yeah, and that's it, no? There's only 2 possibilities, no? So yeah, it seems X does, and X is equal to X, no? And here, X or X, what happens when 0 and 0 is 0, 1 and 1 is 1. So yeah, it conforms to these properties, no? Now there's another 3 laws that are not here, but that are also very, very useful. One of those is the identity law. Which says that let's see, X and, well, sorry, this is an ampersand. I don't know how to draw them correctly. And okay, let me try make an effort. Let's see. Okay, great. And the opposite is X or 0 is equal to 0. Does this make sense? Again, let's see. Again, what happens if, for example, in this case, X is equal to 0, 0 and 1. 0 and 1, what is this? 0. So because X is 0, then it follows that this is 0, no? And again, 1 and 1, you already saw that is 1, no? Like here, no? So yeah, it is true, no? That this law exists. And the same with X or 0. Like if you see 0, 0, we already saw that it's equal to 0, and 1 or 0, this is 1, no? So again, you can prove that this is correct, no? But again, this is a very just useful to understand. Then we have also the dominance law, which tells us that X and 0 is equal to 0, and X or 1 is equal to 1, no? And again, it's something similar than as in here. 0 and 0, it's 0, no? 1 and 0, it's 0. 0 or 1, it's 1, and 1 and 1, it's 1. No? So whenever you have a 0 with an AND, like the 0 will prevail, and it result in a 0. When you have a 1 in an OR, like the 1 will prevail. Again, because somehow the OR and ANDs operators are defined. No? And finally, like, we also have the inverse law, which is very useful. Let's see, inverse law, which tells us that X It's, oh, sorry. X and its complement, it's equal to 0 on X or its complements equals to 1. No? Does this make sense? And what happens if we have different values in an AND? No? What happens if we have 1 0 or 0? Sorry. 1 and 0 in an AND, which one prevails? 0, no? Again, because we can go back to dominance law. If there's a 0 with an AND, it's always 0. And it doesn't matter if it's 0 or 1 or 1, 0. Again, we have the commutative property that tells us that order doesn't matter when it's the same operator. And what happens if we have 1 or 0? Which one prevails? 1. Again, we go back to our dominance law, and we say that when you have a 1 with an OR, it will always result in 1. No? So these are also very useful properties. Let me see. Okay, so yeah, I guess idempotence and all these laws, no? I guess, is there any question so far with all these laws? Because it will be very, you will need to basically use them when reducing expressions, and you will need to really understand them, no? To be able to apply them. So absorption tells us that whenever we have an X and an X or Y in a parenthesis, it doesn't matter whatever this X is ORed with, the X will prevail. And its dual will say that X OR and whatever X is AND with, the X will prevail. No? And you can see again, try doing it. For example, we can make our truth table here, no? X, Y. Let's see, I need to share again my screen. Sure. Okay. Okay. Forward. So yeah, 0 and 0. When there's a 0 or 1 or 0 or 1, 0 or 1, in an OR, the 1 will prevail. So this will be 1. And 0, well, this is 0, no? So this is indeed 0. 1 or 0, again, because it's 1 or 0, the 1 will prevail. So this is 1. And 1 and 1, that's 1. And when it's 1, 1, this is 1, 1, this is 1, and 1 and 1, this is 1. No? So you can see, no, that the result of this is whatever there is in X, no? And you can prove it with all these properties. Combining, no, tells us that whenever we have an expression such as this, where the two terms are similar, but one of the literals is complemented, we can just say remove that and just stay with the literal that is unchanged. And the same in its dual form, which is X or Y and X or complement of Y. No, again, in general, if you have again terms that are similar but only differ in one literal, that these literals are complemented, you can just take them out. No? And finally, the Morgan's law, which tells us that whenever you are having a complement of something in a parenthesis, you basically change the operator. If it was an and, you change it to an or, and complement the literals inside. And you can apply this with many terms inside parentheses. No, for example, let's say we have a not x and xy. So this would be equal. We can do it by steps. We first bring this not operator inside, so it will be not x or not x or y. So we have this, and then we bring this not operator inside this parenthesis. So this will be equal to not or not x and not y. No? So does this make sense to everyone? I use a matter of distributing these not into literals and changing the operators. So any problem with these laws? Well, with these properties of Boolean algebra? Because these are the ones that we'll be applying through all our exercises, and it's very important that you know them. Okay. So again, I was talking about the dual. The dual is nothing else than this property Boolean functions have that if you replace ands with ors or ors with ands and zeros with ones, you'll get another valid expression. No? As you can see here, like all these properties, if you get the dual, you'll get another property that is also valid. Now, this doesn't mean that these functions are equivalent. It just means that if you replace these operators and ones with zeros, you'll get another valid property. I mean, for example, in the dominance law, we have that I'll say you replace this operator and you replace this bit, you'll get this. But again, you can see that these are not equal functions, but again, these are valid Boolean functions, you could say. No? So that's what dual means. No? And you can see here again with a more complex function. What is the dual? Any doubts with this? Is it easy to understand?
Is the typical notation for the dual just F with a B above it, like B super?
Yeah. That's one way of writing it. Like you don't actually need to specify it. Like you just can say that's a dual function, but yeah, that's a way of annotating that it's a dual function. Yeah. Okay, no problems. But now we're going to try solving the exercise. So let me just try reducing this so that we can have our table. I'll only have these expressions, but remember that there's also the let me just remember there's also the identity, dominance, and inverse laws that I just annotated there. Okay. Let me just figure out. Okay. Where am I? Okay. So yeah, we need to reduce this expression. And why do we want to reduce it? Because maybe we have this function that has many literals, many inputs, many operators, but maybe we can do something with less literals and operators that does the same, no? And this will
would mean that we are saving on money and energy and whatever, no? Like, you should always try reducing your expressions because that way you can, I guess, saving time and everything, no? Like, not waste resources, no? So, you had a, okay. So we want to reduce this expression to the minimum amount of literals. No? We want to see which literals are redundant, which operators are redundant, and only get what this function really does. No? And the way to do this is through these properties. Like basically you go step by step applying one of these properties until you get a result that seems to be the one with a minimum amount of literals. So what will be like a first step in order to solve this expression?
You start combining one, right, where you basically combine x and y and z and x and y and not z into just x and y.
And let's go step by step, no? So first of all, you could say that in order to put it in this form, we need for these two expressions to be close together. So we need to apply the commutative property, no? This is the only time I'll say I'll use the commutative property because I guess it's not that difficult to understand, maybe. And it's just like in even ordinary algebra. So commutative means that you can just change terms if they are separated by the same operator, no? And so basically we'll express this as this, no? Or x, y, and z, or x and y. Okay, we have it in this form. Now, Seth, right?
Yes.
Seth was saying that we should use the combining, no? But if you see the combining, like it only has two variables, no? And we have three variables here, no? So what I guess a good way of trying to make it easy for you to understand is using variable substitution the following way, no? You can say A is equal to X and Y, and therefore you can express this previous expression, I guess, using A, no? For example, we can have A and Z, or A and not C, and not X and Y, no? So now it seems that this expression conforms to what the combining rule tells us, no? That when only one of the literals is changing, which in this case is the Z, we can remove it, no? And therefore, if we apply again combining, we'll get something like this. What is okay? A or X and Y. And if we remove a substitution, this equal to X and Y or X and Y. Can we reduce it even more? Which property should we apply? Combining, yeah. And combining again, because again, we have this expression where only one of the literals changes, like is complemented. We can see combining here, only one literal is changing. So let's try doing this, combining. So it would be, we only get Y. And that's the result, no? You can see that we had all these logic gates, operators, doing whatever they need to do, but at the end we only needed just one input, no? Like basically what this circuit is doing is just forwarding the value of one of the inputs, no? And therefore staying with this will be a waste of resources, no? Like you can see why it's very important to
simplify your Boolean functions. Is there any question with this? Like any step you want me to explain more in detail? Uh-huh.
If we have some problems that could be specified each, sort of property that we use to, simplify it down.
Like you don't need to specify the properties like here, but you don't need to make it by steps, no? Because obviously there are already some solvers that do it, no? So we need to see if you're really making it yourself, no? I guess any other question? All right. So let's go with another one. Okay, we have this one. This is more tricky and more tedious. It has a lot of parentheses and you'll see. But I guess anyone wants to try which property should we use first? Mm-hmm. The Morgans. How should we do it?
To get, so Y and not Z, or not X and not W. In fact, just not Y and not Z, and C's and not X and W.
So you say we should do something like this. What do we?
Then you have 3 and.
Y or C. Oh wait, and X or something like this.
I'm not sure if you want to do this.
Okay, maybe. I guess the thing maybe you usually just want to use it in such that you get the knots next to the literals. Like usually you don't want these knots to be like outside big terms. So I would suggest that we do stay with this and we don't apply the models, but again, you can apply that rule. But in this case, it will make it a little bit harder. So, but yeah, I guess that could be, no? Anyone want? With which terms?
Well, we could try like the two, I guess, larger terms between the end.
All right, let's see.
This is a lot.
Yeah, this. So we can apply distributive this way, no? Well, this term with this term and this term with this term, and we can see what happens. Let's see. And X, Y, or what was it? Oh, the same. X, W, and Z, and not W. Okay, we have this expression. What could we do next?
I distributed again.
Which terms?
Start on the left side, I guess, with the X and not Y.
I guess we can do the same here and here. So let's try doing that. Again, we'll have a very large expression, but that's part of the That's why usually you just not do this by hand, you just apply other methods, but this is just for pedagogical purposes. Okay, we have this with this, no? So it's y, z, and x, y. Okay, this one, or x, w, and x, y, and all of these. I think how many parentheses I have? Orth, and we do the same here. Which would be y and not z, and z and w. Or x and w and z and not w. Okay, now we have this giant expression. I guess what can we do something to eliminate parentheses? Let me just see. I don't know how many there are now, but like usually you can see that all these terms are separated by the same operator, no? So this means by associative property, which tells us that doesn't matter where you put the parentheses, it's the same operator. You can just eliminate many parentheses here, and let me just show you how would it what it will become. Let me just move this. Okay, we have this. We say associative, and we will have the next. Okay. So yeah, we have a nicer expression here, no? Without all the parentheses. No? Yes. Can we do anything else to simplify this? Is this the end?
Because like in the first term, there's like a y and not y, it's gonna be 0.
Mm-hmm.
And then like it's similar things in the second variant.
Yeah. So if you remember our, what was it? Inverse law, I think. Yeah. By inverse law, we have that x and not x is equal to 0, 0. Well, inverse and dominance, no? Inverse and dominance. So y and y is 0, 0 and something is 0. Oh yeah, you can do that. Yeah, you can look to the truth table and see that like these are many ways of representing, no? So yeah, but I guess for these purposes we don't need to go step by step. Like in this case, it's obvious, no? Because it's a constant. But in other cases, like from the truth table, you don't necessarily can see the best representation of the logic formula. No? In this case, yeah, no, I agree. But again, y and not y, 0, 0 and anything is 0, x and not x, 0, 0 and anything is 0, and the same. No, you can see there are complement terms in every. So this will end like 0 or 0 or 0 or 0, and this is equal to 0. No? Green here. So again, you're doing all this formula. Let me just keep it there. You're having this formula, building your circuits with many inputs, so that at the end it doesn't do anything. No? Like having this and nothing is the same. So you already lost time. You already lost money and motivation. And this the only thing that it outputs. No? So that's why it's very important to simplify your functions. Any questions with this? Any step you want me to explain more? All right. Okay, let's try doing A. So it tells you to reduce to its minimum number of liters. No, but it appears it's also already reduced, no? So I guess how can we reduce it even more, no? I guess any guess how can we start approaching this function? It's DA, no? 3A. Let me just. Like what pattern do you see in this formula that maybe we could use somehow? Let me guess. Also based on your formulas. It's a little bit tricky, but we'll see if anyone can discover the trick.
You realize that you're ending x and not x
Mhm.
at some point, so then one of them is going to be 0.
Like this is important, yeah. But right now you cannot use it because these are different terms, y and z. The way combining works is that you need to have similar terms. It's just that one is different. But here it's x and not x, yeah. Like it's the y in this case. But here it's y and z. No, but it will be useful in the next steps. But right now you cannot use it that way.
I guess you can do the opposite distributing.
The opposite of distribute.
Y or X, Y and nuts, and Y and Z, right?
So from here to here?
Yes.
Let's see. No, but you cannot do it because you will need the same term. Oh well, with this z, or
X
with
and Y or Y and Z.
x or y. Okay, let's try it. So this would mean that it's, for example, y. Yeah, no, y on. What was it? Not x. Oh no.
X and Z.
Yeah. X and z. Ah, yeah, x or z. Sorry. But and we still have our here.
Yeah, we use the combining plot, right?
What do we have here? It's
Yeah.
well, we x. Okay, so this is distributive. What else can we use? I guess let's put it in parentheses. Any way of solving this? Keep solving this. So indeed, you can do this. The problem is that, as you can see, sometimes starting to combining operators inside parentheses means you're just making it difficult to simplify it more. So you may want to avoid mixing operators. Like what you want is to combine literals with the same operator and use
separate these big terms with another operator. And this is the thing, no? Like reducing these functions is not straightforward. Like there's many ways you can get stuck or not, no? Well, yeah, you can do this, but maybe this is not the way of doing it. Any,
What if you, instead of you, not X and Z with X and Y,
not X and C, and which one?
and X and Y?
But as you can see, you cannot do it because you have to have the same term repeated, and you don't have any same term repeated here. Is it? Can you see? Like you were saying these two terms, right?
Like, distribute, like treat X negative X and Z as like one.
Oh, oh, this and with this.
Yeah.
Okay, let's see. Let's say A is equal to X, not X, and Z. So let's, all right, sorry. Let's assume this distributive. So it would be distributive here, no? Oh, well, it would be the other case, no? But it would be X or no. Yeah, X or not X and Z and Y or not X and Z and everything or Y and C. But as you can see, we are running more or less in the same problem with this, that we are starting to mix operators here, and that may make it a little bit more complex to simply, like you can say we are making it a little bit complex more than simplifying. But yeah, yeah, you can apply this law, no? But again, you're maybe not the best, maybe. Any other guess? Any other try? Maybe. Like this is a tricky one, no? So don't. It's okay, no, to not know. With these two terms? Well, you'll get something similar to here, no?
But you get two terms with, you get two terms X and Y, so you can use that.
Well, let's see. So it was one. Okay, distribute these two terms, right?
Yeah.
Okay, let's see. So we have Z and not X or Y or X and Y. So can we do anything more with this?
We can distribute
This one? Well, you want to distribute this? Let's see. Let's see. We can distribute. So it will be Z or X. Oh wait, no, wait. Oh no, it's what am I doing? Yeah. If you treat X and Y as A, X and Y, and what was it? Not X or Y. No, wait. X. Oh, and X. What was it? X. And X or not X and Y, no? Yeah, no.
I think the second one will be just X and
Wait. It's X, C or X and Y, and yeah, no.
yeah. When you load.
Oh, okay, yeah. Yeah. I got it. Yeah, because this way it will be now interesting. No? Oh wait, which one? It's just I copied the same. Okay, can we do anything else with this one?
The thing again is that we are mixing operators and it makes it a little bit difficult.
So I'll tell you how you actually solve this because it's using neither these ways, but again, I'm glad you are already understanding how all these rules apply. Let's just, well, maybe I should just keep it there for reference. So the way you solve this is that, as one of your classmates was saying, like,
Yeah, you have this not X and X. No? Could we introduce somehow an X in here so that we can now use these terms in order to do something with this?
and let's see how that works. So how can you introduce a new literal inside a parent or inside a, how can you just insert a new literal? Any guess using one of our laws? Well, properties.
I guess you need to like end it by one.
Uh-huh.
So you have to end it by an equivalence, like, I guess, or X, or not X is one of them. There's another one.
How we can apply first of all identity law? Which tells us that X and Y or X and Z or Y and Z. And here's where we add one, no? Like identity law tells us that Y, like A and 1 or X and 1 is X, no? So it doesn't matter if you and it with whatever you want with and, it will always be whatever it was in here, no? Okay. So how can we transform this one? Well, we have the inverse law. And let me just put it here. Inverse law. Well, these are not laws. I don't know why I'm keeping saying that, but or are they laws? I don't know. Well, let's just inverse property. X and Y. And let's see. So this one, again, by inverse, it's equal to, you could say X or X, no? X or not X is equal to 1, no? Let me just put it here. So X or not X is equal to 1. And Y and Z. Does this make sense to everyone? And now it's just a question of this last term using distribution. X and Y or 0. And let's distribute. Well, let's assume this is parentheses. Let's just do it this way. So you would be, what's it? Yeah, X and Y and Z, or not X and Y and Z. Okay. Now by association, we can remove these parentheses and have our formula this way. So what can we do now that we have these extra terms that may allow us to do something? Any guess? Any guess?
You can combine the.
Which one? These last two? Yeah, we can combine them. But what happens if we combine them? If we combine them, we'll go back to this, no?
Oh, yeah.
So back to the same problem. Yeah, you can also be like go in loops, no, with all these properties. So we may want to instead apply them to combine them or apply it along with property with these two terms, no? Or which one can we use? There's one in here that I think we haven't used, or we have. Or how we use? Yeah, I guess. Which one do you think we should use? Uh-huh. I gotta remove it.
Yeah, I think it's,
Yeah, right. So let's see. Again, let's just do a variable substitution. Let's say a is equal to x and y. And let's say b is equal to x and z. So we have, let's rewrite this as a, b, and this is a and z, and this is b and y. So if you have absorption here, what does it tell us? That, well, I'm going to use a little bit. Okay, I cannot do it. Well, if you follow from here, you can see that this should also be x, no? So we have a and z, as in here, where z is the y, and we have a. Again, you can use commutative also to just change them place. And you said that you'll see that you just stay with the a, no? Search. And the same with the b, no? You see b and y or b, that's in here. So the b will be the result. So you basically will have a or b. And this is equal by remove the substitution to x and y. I know what I'm doing. X and y or x, not x and z. Hang on, let me just check that it's correct. Yeah, no. Where's my? And so yeah, like I guess you didn't reduce it in number of literals, but you did reduce it in number of operators, no? So this is the solution. So yeah, I guess any question with this, any step you didn't get? It's a tricky problem. But again, this is a type of logic formula. Like you can see, this one is solved exactly the same as the A one. You can see that to apply all these like steps, you need to understand to see that if there's any variable literal that is in two terms, but it's complemented, and there's this literal is not in the third term, and again you do the same with A, no, as we did with X here, no, similar procedure, no, with this kind of simplifications. So I guess any question on them? All right. Now, dual functions, normal form. So they are now asking us, first of all, to get the dual of this function and then write it in disjunctive normal form. So first of all, what was the dual? The dual was changing operators and changing zeros with ones or ones with zeros. No? So let's write the dual of this function, fd xy, and this is x or not y, and x or y. Okay, that's the dual, no? Again, it's just following the rule that changing operators, and if there's a 0 or 1, just flipping those values, no? Any problem with this? That's the dual, no? Now, again, the dual is not the same as this function. Just take that into consideration. So now they are telling us to do it in disjunctive normal form. What we have in here is the conjunctive normal form. No? Conjunctive means that terms are separated by ands. Disjunctive means that terms are separated by ors. Ors. Conjunctive, and this is how to say I don't know, like expressed as DNF, no? CNF is with ands, as it is in here. Now the normal form always have all the terms in each, all the literals in each of the say terms or parentheses. Again, this function uses only x and y, so x and y should be in all terms separated by these ands, no? In this case, or ors in the disjunctive normal form, and this should be a unique function to the that describes this. A unique expression that describes this function. This is also called sum of products, like this disjunctive normal form, and this is called the product of sums. No? This product of sums because it's a product of sums. No? Well, how can we translate it into a sum of products? Well, you can take the complement of it, and you'll get the sum of products. No, if you get the complement of this. It will be this way, no? X, well, we have this, X, not Y. Which is equal to not X and not Y, or not X and Y. And then we further, again, using the Morgans, we have that it's not X and Y, or X and not Y. No? And you can see now it's a sum of products, which is a disjunctive normal form, because it's a sum of products. And these the two forms you express a function, the canonical forms, I think they're called. The normal forms. Again, this is the DNF. And this is the CNF. These are just complements of each other. And again, the properties that they need to have all the literals in each of the parentheses, separated by the operator that is or and. No? Yeah, I guess any. Wait, I think I didn't. I missed a step here. I think it's X and not Y. Wait, what I'm doing. Did I do something correct? You need to complement all the variables. What's happening? I think I made a mistake in here. Where is it? Where is it? Okay, I guess. Okay, I guess the reasoning is incorrect. Let's just make it again. Sorry for this. So I guess well, I guess when you want to do these disjunctive normal forms, you more than anything take into consideration which combinations are being represented here, and the disjunctive normal form is basically the other combinations that are not present there, not which is the complement, but not the Morgan's complement is the I guess the complement of combinations, no? So you could think like instead of this, let's put it like this. So basically you just see which combinations are missing here, which is so in here you could say combinations 1 and 0 are represented and 0 or 1 are represented, because if you see 1 or 0, it's 1, and whatever well, I guess and 1 and no, if it's 1 and 0, 1 and 1, and 0 and 1. Well, see, 1 and 0 and 0 1. Wait. Oh no, because this is the CNF. Okay, it's the opposite. So it's 0 and 1. So this means it's 0 and 0, 0, 0, 0, 1 and 1, 1, 1 and 0. This is equal to 0. So I guess we'll go to the next examples. So because this example may be tricky, but I guess you'll understand this in the next example, because I think this is not the best way to explain it. But yeah, don't worry. Just I'll put the detailed procedure here in the slides, though, so don't worry. We'll go into this deeper in the next slides. I guess we can, just to address that problem, let's see how we can in fact create the sum of products and product of sums using the truth table. So we have this truth table. It has 3 literals, and you can see that for each you can express it as rows, and each combination gives you a 1 or 0, no? So they use a way of getting the sum of products or product of sums. Again, the sum of products being the DNF, and the products of sums being the CNF. Is by, let's go with the DNF, is by looking to all the rows that have a 1. So you can express the DNF as a sum of products by using this notation, no? And getting which rows are the ones that have a 1, no? So in this case, it's the 0, is the 0, 1, 2, is the 3, and 6 and 7, no? Those are the ones with a 1 in here, no? 0, 1, 2, 3, 4, 5, 6, 7, no? So those are the ones that have a 1 in place, that resulting 1, no? And if you want to express it as with literals and all that, basically, again, because this is supposed to be a disjunctive normal form, which is a sum of products, basically just look at the literals and see, in this case, the result, the 1 that is here is the result of A being 0, B being 0, and C being 0, which means you would apply it, describe it in this way, no? Okay. Which would be not A and not B and not C. So again, if you put this combination here, it should result in 1, no? Like 0, 0, 0. It's 0, 1, B, 1, C, 1, no? So 1, 1, 1 is equal to 1. So this function will result in 1. Or we can see the other combinations, which is 0, 1, 0. So this will be not A, B, not C. And if you try this with combination 0, 1, 0, A equal to 0 is with not is 1, 1, and not 0 is 1. So this would be 1. And if you put another combination, this should result in 0. All these functions should give 0. But again, we keep adding all the other terms. So this is so the other one is not A, B, and C. And then we have the other two, which is A and B and not C. Or A and B and C. So this is the disjunctive normal form, no? Which is the sum of products where all literals are in the parentheses, and all these terms between parentheses are separated by ors, no? And again, if this will only result in a 1 if you put any of these combinations, but if you put any of these combinations, it will result in 0. So this is a way of expressing the function that is here. Is any problem with the notation here? You're just first of all looking which rows are ones. Each of these rows are called the mean terms, and mean term is expressed, I guess, with literals in this way. This is each of these is a mean term, and each of these is separated by an or. And again, this function is what's called the disjunctive normal form and expresses what this truth table is expressing. No? So I guess, does it make sense? But we can simplify it, no? Again, this is the canonical form, but this is not the reduced form we can get, no? So how can we reduce even more this function? Any guess here? Which properties should we apply? Which ones?
We can combine this into we can do it in the last two terms.
Last two terms.
And then
So they only differ by one the literals.
Yeah.
So you can apply combining. No? Again, you can do substitution of variables. You can say A is equal to A and B. So you have A and not C and A and C. Well, I guess let's choose another variable. Let's see D, no? D is equal to A and B. So you will have D and not C and D and C. And by this property, D and the same variable but complemented, you get D, which is A and B. No? So you can do that. Not A and B. Not A and B. Yeah, you can do this. Exactly. I guess you can choose which one, no? You can choose to use this with this one or this with this one. So let's just keep the first one intact and apply combining. So let's see. Not A and B. That's it. And we apply combining this with this one. So this would result in not A and B. And we apply this with this one, combining again, and we would get A and B. What can we do next?
Apply combining on the last 2 terms.
Exactly. not B, and not C. So you apply combining here, you see that the only one that changes is the A, so you stay with the B. Can we reduce it even more? Any guess? Let's distribute. Where is my distribute? So we get A and B and B or B, right? And not C and B. Can we reduce this even more? Yeah, no, this is by the inverse law, this is equal to 1. And 1 with and anything is anything, no? You say. So this is equal to not A and B and not C and B. So yeah, this is the reduced form, no? Let me just check. Yeah, no? Okay. But you know, you can also get the same formula by using the max terms. And the max terms are those expressions that result in 0. And let's see how this works. So let's see all the rows that have 0. It's the 1, 4, and 5, no? Which is less, no? So we can express the product of sums, because this is now the case, by using 1. Which one do you? 4 and 5. And you can see that these are you could say the complement of this set, no? The 0, 1 is not present here, nor 4 and 5, no? So this is the complement of the set in here, no? Now you need to express this as a product of sums using the max terms, no? And the way this you can do it is by checking again the combinations 0, 0, and 1. In this case, you apply inverse logic, so it will be A or B or not C. No? So in this case, again, you're applying inverse logic, so it's A, 0, it's A, you could say 0 is B, and not C is 1, as it's here, no? And again, if you apply this combination in here, 0 or 0 or 0, yeah, 0 or 0 or 1, which is complemented 0, yeah, that should result in 0, no? And any other combination may not result in that, no? And A, not B, and not C, no? Let me see. A, not B, not C. And this is the product of sums, no? A, no, wait, what I'm doing? No, it's the opposite, the opposite logic. It's not A, and this will be not A, B, and not C. Yeah, no? Not A, B, and C, not A, B, and C. Okay. So in this case, we only have 3 terms as opposed to the 5 we have here, no? And again, this is the product of sums, which is the conjunctive normal form. And we can simplify it again, no? What can we do? Well, combining again, no? Let's use combining. I will get, for example, we can combine this and this. And we'll get this and this. We see that A and B, not A and B are the terms that are in both terms. So it's A and B by applying combining. Okay. And then what else can we? So we can distribute, maybe, let's see. Distribute, we'll see, I can see that we are distributing, yeah. No, or should we do this? Yeah. Let's see, it will be A and B and not A, or what was I doing? Oh, no, wait. Z complete. And not A, or maybe this is not the best way. What do we have here? What do we have? Let me see. B and, or should we distribute this with this one? Yeah, because it's two terms, no? Right? A and B and C and B. All right, yeah, I think we can do something here. So we have this, or we have this. Let's see, which can we use? Absorption. We can use absorption here because we have B and, oh yeah, the other way. No, yeah, we have this. So absorption we can apply in this case because you have B and B or something else. So this should be B. And here, here I guess we can distribute again. So we would have A and not A. We would have or B and not A. And we would have or not A. Not A and not C. Okay, so this becomes 1. And what else can we do? So we have basically B and not A. Okay, I see. And A and not C. And B, no? Again, we can apply absorption. So we can remove this term. And at the end, we will get that our expression is this one. This is our expression. And you can see it's the same as the last one, no? Like this and this are the same. This is just like this distributed. Well, you just distribute this and you get the same as here. And yeah, this means that you can get the same formula either through max terms or midterms, no? Minterms, no? Like they represent the same thing. But you usually want to use the formula that has the least amount of elements, so max terms, midterms, no? To simplify your life. I guess, does it make sense to everyone? Any step that you didn't get? It's just a matter of applying each of the properties and getting to something. Any question? Okay. So let's see. Now we want to convert an expression to normal form, which is, again, the normal form is one where we have something like this, if it's a product of sums, or we have this, if it's a sum of products. Usually when they tell you normal form, it's a sum of products. So this means well, it's already like in a kind of sum of products because it's separated by an or, which is taken as a sum, and there's product here. No? But we have 3 literals. We want to have terms with 3 literals each separated by or. So we not need to insert variables into each of these terms, the ones that are missing. No? So what do we need to use in this case? That we already saw in one of the examples. How can we add the missing literals to each of the sides of this? Well, to each of the terms in this logical expression.
Identity with that. But not or.
Use identity and inverse, no? So basically what you do is, okay, we have A, and let's use identity and just put these like ones that behave like placeholders. Again, because you can AND something with an one and it doesn't matter. And the same here, no? Or 1 and not B and C. Okay, now we will need to use the inverse law to just replace these ones with the variables we want. Okay, this was with identity. No? So we use inverse to put the variables we want. So this is B and not B. This is C and not C. Or A or not A, and not B, and C, no? And now it's just a matter of distributing, so that's the tedious part, no? So everything after this will be distribution. So let's see. We have, first of all, A and B. Let's put this here. A and B, or A and not B, and all these ands with C and not C, or we apply distribution here. How should we do it? Maybe let's. What can we do? Put parentheses here and say A and not B and C, or A and or not A, not A, and not B and not C. Okay, we have already here 2 terms that already conform to what we are looking, but now we need to develop this, no? So again, distribution. So this means that it's so let's see, it's A and B and C or not C, or A and not B, and C or not C, and everything else, no? Which was this one, and then finally we distribute again, and we'll finally get all the terms, no? So this means that it's A and B and C, or A and B and not C, or A and not B and C, or A and not B and not C, or everything else, no? So we have let me just another. So we have 1, 2, 3, 4, 5, 6 terms, no? Which are these ones and these two, no? But can we somehow reduce, like, you can see there are some repeated elements, no? And what happens if we have repeated elements? What property can we apply? We have repeated elements separated by an and, by an or, sorry. So x or x is equal to, what property is it? Yeah. So you can see these two are the same, no? Let's see if they're other equal. Okay, no. So yeah, you can just take only one of those, and this will be the solution, no? Oh, okay, not be. Yes. Wait, there's a missing one. Not A, not B. Just check. Wait, did I mix something? Did I mix something here? Oh yeah, I think I don't. Yeah, this not C. I don't know where does it. This shouldn't be here. Okay, so it should be C. A not B C. A and B are not C. A and not B and not C, and not A, not B, and C. Yeah. So this is the solution, no? And this is if they ask you for the normal form, but you know you can do the inverse and get the reduced form, which would be this one. But this, I guess, the expression that identifies this logical function. Is there any question with this? And here is like
What they tell us, no? Like each input variable appears exactly one in each term, and we can use that to compare
whether two functions are equivalent. Let's just do a last of these exercises. Let's do this one. So write down a simplified Boolean expression for the functions computed by the logic circuit. Okay, we have this logic
circuit, which is another way of representing the logic function. Again, we have logic gates, we have truth table, we have the Boolean expressions. So how can we express this as a Boolean function?
Any guess? Like we already know, well, we can say these are intermediate inputs A and B. We have X, Y, and F, no? So F, with respect to A and B, what it is? What is this gate that is here? Anyone knows which one is this? What?
Yeah.
NAND, exactly. So the way you express it is just F equal to A and B, but it's NAND, no? So it's the complement of this of the AND, no? Okay. What is A equal to with respect to X and Y?
X complement or Y.
X complement or Y. And B is the opposite, no? B is X and Y complement. So we just substitute here. Basically not X and Y, and X or y, or not y. It's a substitution, and then we apply the Morgan's law, no? Which would be we just take this knot and like you can leave it like that, like it makes sense, but I guess we want to be sure like knots, the knot operator is always with the literals. So by De Morgan's, we just okay, we can first try doing it this way. Or not x y, and then we apply further the not operator, so it would be x y no y. Okay, does it make sense to everyone? What does this function does like? I guess is this like which gate is this in fact? Exactly, this is the XOR. So as you can see, we can build other gates using other gates, no? And this is the XOR exactly. I guess any problem with this? If not, I guess this is the same. So how about you just you can do the attendance form, so you have time to do it. The problem in here is exactly to one, well, not exactly, but it's very similar to one of the ones we did in right now. So yeah, just take your time. If you have questions, you can raise your hand or whatever.
Sure, it's the
Well, first of all, everyone just already got the link. Anyone missing? All right. Which one? Sorry.
that was just the.
The tables. Okay. Yeah. And whenever you finish, you can go. Oh yeah, sure. Let me just how about I put this here. The attendance form. Is it okay? Okay.
Yeah, I got it.
Perfect. And it's pretty similar to one of the ones we did. And with a trick again. Remember that trick?
And just as a side note, like the way you transform from conjunctive to disjunctive is just distributing, as you can see here, like we have the dual here. And it's already in conjunctive normal form, which means as a product of sums. And we want to get it as a sum of products, we just distribute and we'll get it to this, no? And you can see that the set of combinations that they represent is the complement of the set of combinations they represent. Like here it's 0, 0, no, sorry, 1, 1, and 0, 0, whereas here it's 1, 0, 1, 0. So it's like different combination, no? But that's the way you transfer from CNF to DNF, no? Sum of products to product of sums, and that's the way.
You have a question about
Both. This one?
Some of products are just fine.
Yeah. Yeah. Was You know what?
You just so then QR code.
Oh, yeah. Anyone did not finish? Well, it requires more time. Anyone requires more time for the attendance? No, okay. Or 1 submitted? Alright.